hundreds of millions of dollars, 710,000 square kilometers mapped and scoured. Yet the final resting place of Flight 370 remains unknown. This effort involved the most sophisticated research vessels and deep-water sonar systems on Earth, culminating in the most expensive underwater search in history. The official Australian Transport Safety Bureau report concluded that after running out of fuel, the Boeing 777 entered an uncontrolled high-speed dive into the ocean. What if the official math itself is wrong? A growing body of independent analysis suggests the aircraft didn't simply fall out of the sky. Instead, the physical evidence points to a controlled ditching. By cross-examining the raw data, re-evaluating satellite metadata, mapping radio signal anomalies, and tracing deep-sea acoustic signatures, we can reconstruct the flight path through the lens of physical evidence. After flight MH370 vanished from civilian radar, investigators reconstructed its final hours using automatic satellite handshakes, specifically burst timing offset, or BTO, data. This chart shows how BTO handshakes formed probability rings across the Earth, calculated by measuring distance between aircraft and satellite. The final handshake at 0019 UTC established the 7th arc. This curve across the southern Indian Ocean became the focus of the massive search. To narrow down the impact point, the ATSB analyzed a second metric, the burst frequency offset, or BFO. Their model assumed the final Doppler shift indicated vertical acceleration, meaning the plane fell straight down the moment the engine stopped. This bathymetric map illustrates the intensely searched zones along the 7th arc. Searchers mapped the exact impact area predicted by this vertical dive theory, but found the seafloor to be completely empty. If the ocean floor is completely barren, exactly where the math predicted, then the model used to guide the search relies on flawed assumptions. The ATSB relied on a motion-decoupled up-down model, which assumes the aircraft became a dead weight accelerating straight down with gravity. An alternative declination model couples horizontal and vertical motion, allowing for a continuous glide. If a 300-ton aircraft enters a supersonic vertical dive, the kinetic energy upon hitting the ocean surface causes it to shatter into millions of small fragments. A crash of that magnitude generates a massive buoyant degree field. Yet surface searches across millions of square kilometers within the 7th arc zone recovered no floating wreckage. The physical evidence we do have washed ashore thousands of miles away. Air crash investigator Larry Vance conducted a mechanical analysis of the recovered flaperon. The specific damage to the trailing edges of these wing components only occurs if the wing flaps are extended at the moment of water impact. Extending wing flaps is a manual action that requires a pilot to manipulate the controls. An automated ghost flight cannot execute this configuration. So while yay, the question is, why search based on a vertical dive when the physical evidence requires a glide? The physical evidence of extended flaps indicates a controlled ditching. This configuration is incompatible with the ATSB's high-speed vertical crash model. The evidence for an active pilot begins long before the flight. Data recovered from the captain's home simulator reveals a clear environment of premeditation. Investigators found deleted simulator coordinates plotting highly specific routes. These tracks targeted some of the deepest, most remote parts of the southern Indian Ocean.
An independent group of researchers has proposed another data stream to analyze the flight path: WhisperNet, a global web of amateur radio signals. While the methodology is subject to debate, these researchers have identified 186 signal disruptions that they suggest align with MH370's estimated flight path. Their analysis suggests these disruptions map out a precise circular racecourse holding pattern centered around a specific navigational coordinate known as waypoint Pakra. An aircraft operating as a pilotless ghost flight on autopilot flies in a straight line. It does not initiate and maintain mathematically precise circles. So think about it. Entering a holding pattern requires an active pilot waiting for a specific time or event. Corroborating the simulator tracks with these radio intersections challenges the ghost flight theory, suggesting the aircraft followed a calculated route. To locate the end of that route, we turn to the SOFAR channel, a deep oceanic layer where sound waves can travel for thousands of miles.
When a 300-ton Boeing 777 impacts the ocean surface, it generates an immense acoustic signature, detectable by international monitoring stations. This spectrogram shows data from hydroacoustic stations AH01 off Australia and AH08 in Diego Garcia. Around the exact estimated time of the crash, both stations recorded distinct frequency anomalies. Official reports characterized these sounds as natural Antarctic ice cracking. However, independent researchers noted that the arrival times of these sound waves did not match the speed of sound through water. This timing paradox is resolved if the impact sound waves initially traveled through the solid seafloor crust, carrying sound twice as fast as water. Tracing these sound waves backward leads directly to a 6,000-meter deep trench known as the PL Deep Hole. The precision of this origin point is significant because it mirrors the exact deep-sea coordinates recovered from the pilot's simulator. This leaves a stark contrast between the massive, generalized search grid and a specific origin point generated by these acoustic readings. The hydroacoustic physics point to an impact within a specific deep-sea trench, a location that matches the high-precision targets found in the captain's flight simulator. The official fuel starvation dive model failed because it ignored the kinematics of horizontal glide and isolated satellite data from the physical evidence. When we examine all the available evidence together, a consistent picture emerges. First, the Inmarsat satellite data gives us the seventh arc. Second, the WSPR-net radio analysis identifies a holding pattern leading right up to that arc. Finally, the hydroacoustic triangulation lines converge on a single geologically deep trench just past that arc, the PL Deep Hole. This alignment of independent datasets describes a flight path maintained by human input until the final impact. The overlapping math of three independent datasets forms a consistent model of the flight's end. The data describes a flight that remained under human control until its final moments. The ocean is vast, but science can never lies. Dedicated searchers continue to look for the truth, relying on advanced marine robotics and precise geological targeting. The investigation reached an impasse not because the wreckage is unreachable, but because the search area was dictated by a model that assumed the plane simply fell. To finally close the case on MH370 and bring peace to the families, authorities must move past the flawed vertical dive model and follow the physics of a controlled ditching.